Hello, Stats 300, and this is Professor Gonzalez, and I would like to go over some problems in the assignment side of ALEKS 11.1, which is covering hypothesis testing for the difference between two means, and these are independent samples. Okay, we have two problems we're going to do. Let's see, I'm trying to think if there's anything extra I want to talk about. No, I think we can just dive right in on this. So for me, one of the big things about this is really organizing your data, keeping things really organized, maybe even using color to do that, because we're talking about two different means that we're looking at, two different samples, two independent samples, okay? And this section specifically is looking at the two different means of those two, or trying to say something about two different population means given the collection of data from two samples from those two different populations. Okay, and so this statement here, where we have the null statement and the alternate statement, alternate hypothesis, instead of saying something like the population mean is going to be equal something, right? It would be comparing. It'd be saying the population mean from the first population is going to be equal to the population mean from the second population. So you're going to be comparing two different means rather than just saying a mean is equal to or greater than something like that. Okay, so that is a big difference. But other than that, a lot of it is going to be very similar because we're still going to be doing hypothesis testing. And the test statistic for looking at hypothesis testing for the difference of between two means uses a t distribution. Okay, so we're just going to kind of focus in on critical value testing rather than doing p-values also, just because our charts are not as accurate with p-values when we're using a t distribution chart is what we have. All right, well, let's start to organize our data. And I think the first thing I want to do is change over to a red pen. And let's look at this. It says a researcher polled a sample. So now we're already talking about a sample. I'm going to mark this as the year. Okay, so I think I'm going to write that right here. I'm going to say 2010. So it says a sample of 1,015. So n equals 1,015 adults in the year 2010, asking them how many hours a week they spent on the internet. Now it says the sample mean. It says the sample mean. Now we know sample mean is x bar. The sample mean is 10.59 with a standard deviation. Now remember, this is a sample, so sample standard deviation, so it's little s, equals 14.58. A second, so we're going to use a different color here. It says a second sample that's done in the year 2012, so a couple years later, has a sample size of 1,088 adults, and they were asked, let's see, in the year 2012, for this sample, the mean, so now we're talking about sample mean, so that would be x bar. It's really important to get your variables straight, so when you plug them into the formula, everything matches up nicely. So this is x bar, and that is 9.62. I'm just still talking about the sample, so the sample standard deviation, a little less from this second sample is 13.72. Assume these are simple random samples from a population of adults. Can you conclude? So now we're getting into, our alternate hypothesis, right? The statement. can you conclude that the mean number of hours per week spent on the internet decreased? Now, be really careful. Remember 2010 we're showing as red. 2012 we're showing as green. And what's kind of nice about this part of ALEKS is that, let's see, is that they define, whoops, that just took off on me. They define mu1. So, because you're going to have a mu sub 1 and a mu sub 2. And they just define it for us. Because if they don't define it for us, then you have to define it. And sometimes you might say something's less than or greater than, depending on how you define it. So this just kind of makes everything kind of unified for us. It says the population mu from our first group is going to be denoted as let's see, the number of hours spent on the internet in the year 2. So essentially this 2010 is lined up with M sub 1. So that would be a good thing right here to realize that these are all going to have our subnotations of 1. And then they tell us, they don't tell us the other side. So the other side is then it's assumed that 2012 must be M sub 2. So all these other guys in our formula would have sub 2s on them. Okay, so that's good to get straightened out. And another thing that's a little tricky, more tricky on this particular wording than others, I think, but it says the hours per week spent on the internet decreased. So we're trying to conclude this. We're trying to use this in our alternate hypothesis that the internet decreased between 2010 to 2012. Well, if it decreased, that would mean that if it decreased, that means that in 2010 it was larger, or was large, just to kind of get our ideas flowing. And then it decreased, so this must be smaller, right? So what kind of mathematical symbol can we use to show that? Well, if this is large and this is large, my pencil's not working. If this is large and this is smaller, so this is large and this is smaller, of course, we could have a greater than symbol that would do that. Okay, so that's going to be our alternate hypothesis. Remember, just like hypothesis testing before, this always has an equal sign. This has an inequality or not equal. Well, in this case, it's going to be greater than. So we're going to say the population mean from population 1 is greater than the population mean from population number 2. And just like always, the null hypothesis is going to be equality, that they're equal. So we're going to assume they're equal. We're going to run through our statistics and see if we can reject the null and go with the alternate. So because this is a greater than symbol, this is going to be what type of test? It's going to be a right-tailed test. Okay, so we got all that great information that I got to refer back to. Okay, let's see. Next. How many degrees of freedom are there? Now this, using the simple method. So what I want to do is write down, remember degrees of freedom is always going to be based on the sample size. The thing here is we've got n sub 1, sample size is 1015, and then we got in green, n sub 2 says the sample size is 1088. So the way that the simple method works is that you look at your smaller sample size, 1088, 1015 is the smaller one, and then just do your typical degrees of freedom is 1 less than that. So my degrees of freedom here is going to be 1014, and that's that. Then we move on to the next step where it says find the critical values, round your answers to at least 3 decimals. There's more than one critical value. Then separate that with commas. Well, this is a right-tailed test, so let's, I think a picture is going to be worth something here, so let's do that. So if I go ahead and take a look at my normal distribution, my standard normal distribution, and remember, how do you know Well, right there is a t. That's how you know it's t. But how do you know that we're talking about t distribution? Well, probably the biggest, if you forget, you always go to your formula sheet, and this says, where's that? Oh, there we go. It says two sampled hypothesis testing, and there it is, difference between two means, and there it is. It's a t value test, okay? So we know that everything, if you're going to refer to a table, it's got to be the t table, t distribution table, or student distribution. Let's take a look at this just to kind of get our ideas flowing here again. We said that this is a right-tailed test. So we're looking for the critical value of this. Now, they told us somewhere an alpha level. I didn't pull that out yet, and there it is right there. We're looking for an alpha significance level of 0.05. That means that this alpha is, this alpha is equal to 0.05. We want to know what this critical value is, which is sort of the, deciding the point of either reject or don't reject. So anyhow, what is that value? Well, we could look that up. And the beautiful thing here is our t distribution, when we look at it, it always gives us area to the right, and that's just what we have right now. And, it usually goes with these common alpha values. Let's go check it out. So the things I need to know is I need to know alpha, area to the right is 0.05. I also am going to need to know my degrees of freedom is 1014. Let's look it up. So we go to our t distribution table. You can see it right there, t. There's my t distribution, so you got to be really careful to use the right table. And this table always gives you area to the right, correct? So that's important to know. And the area to the right, is listed, area in the right tail. Well, we're looking for area to be 0.05. 0.05, area to the right is 0.05, so that's what we need. Now we need to go down to degrees of freedom of 1014, and the biggest this chart goes to is 200. It basically says if your degrees of freedom are greater than 200, well then just use z values, because when our sample size gets large, the values of a t distribution basically become a z distribution. So once we're that large, we just use the z values rather. And so, where am I at? Area to the right is 0.05, so we go down here to see what t value goes with that. And we can see that the t value that goes with that is t equals 1.645. Okay, let's get back there. There it is, 1.645. So the critical value is t equals 1.645. Okay, next up is we need to calculate our test statistic. Now that test statistic, we remember I already showed you where you can find it, and that is going to be on our formula sheet. And two samples, difference between two means, there it is right there, that beast. Oof, okay, now something to note that is consistently going to be true is that when you're doing the two sample hypothesis testing for the difference between two means, look back here, it's always going to be true that our null hypothesis is always going to be equal, saying the two different means are equal. They have the same value. That's our assumption that we start with until we prove it different. So when we go, if the mean from population 1 and 2 are equal, guess what that does on our formula? Well, if this value is equal to this value and subtracting them, guess what that is? Right? That's always going to be 0. That's always going to be 0. So, that'll just go away, because then you subtract 0, subtract a number minus 0. It's just going to not do anything to the value. So that can be disregarded, but I will write down the formula just to kind of get us to start trying to remember that formula. I don't have a lot of space to work here, though. That's the only problem. Let's see, how much do I need to fit in there? Okay, it's going to be a little bit tight. I'll write it down, and that formula is, in the numerator, we have our sample means, so x bar sub 1 minus x bar sub 2. We got to subtract that, and then we have to subtract that from mu sub 1 minus mu sub 2. Whoops. But remember we said that they're going to be equal values, so it's just going to be 0 there. So that just goes away. Don't even have to worry about that. Down below is a bit of a mess. We have our sample standard deviation from first population. That gets squared, divided by sample size from the first population. And we have our standard deviation, sample standard deviation from our second sample, and that gets squared, and that's divided by the sample size from the second sample, and all square rooted. So very easy to forget to square. That's a common mistake. And the way you put these values in calculators, you got to be kind of careful. You're going to have to just divide first, find these two fractions, and then add them up, and then square root them. So you got to be a little bit careful. Let's go ahead and put this in. I'm going to try to put this in using some color, at least this first time or so. So remember, the first thing is going to be the sample mean of 1 and sample mean minus sample mean from 1. So sample mean minus sample mean. So the colors here, I'll go ahead and use the colors. So that is going to be, my sample mean from the first sample is going to be 10.59 minus sample mean from the second sample is going to be 9.62. And then that other piece, remember, is just going to be 0. Subtracting the two means, it's just going to be 0. Then we have this big square root symbol. We have this fraction plus this fraction, and these numerators getting squared. Just doing all that so I don't have to go back and forth with color too much. And what we have here is we have our standard deviation from the first sample gets squared. Standard deviation was 14.58, which gets squared over our sample size from the first, which is 1015. Then we take a look at our second sample, and the sample standard deviation from that is 13.72, and that gets squared. Sample size from that second sample is 1088. Okay. Let's show some of my intermediate steps here for you so you can kind of follow along, make sure your calculator is doing what you think it's doing. We end up getting 0.97 in the numerator. Down below, I figured I squared it and then divided it. And so that gave me, so I've got to take the square root of this, these two big numbers are not big, but I'm not rounding much at all because I'm trying to use as many place values. We've got 0.209. So I'm just going to show you all this value so you can see it on your calculator. 20943,487. Right, and that goes forever, plus 0.173013 2353. Okay, so you sum those up, take the square root, and then you do this division problem. And let's see, I guess I showed you a little bit more on this one. So then up top you still have the 0.97. Down below you've got 0.618423888. Find its quotient by dividing 1.568 and now let's go ahead and round to 3 decimal places, and I'm going to get my t value, right, is going to be approximately 1.56 and rounds up to 9. So there's the answer. Now they're asking, determine whether to reject. Okay, now is where it gets tight with the picture. I think I left a little bit of space to do this, which is good. We've got our standard normal distribution. Of course, this just is a t distribution. We still have our 0 in the middle. And on this particular problem, it's a right-tailed test, and I've got my critical value right there. So let me redraw. I don't have to redraw. Oh, well, I'm doing it now. So then we've got this. Oh, and then it erased. Go back. So we're doing this with critical value. We're saying that critical value right there is 1 point, what was it, 1.5, no, what's the critical value? 1.645. So remember, the further away from 0 is going to give us evidence to reject. And if we get past this critical number, and we are actually land into this unlikely region over here, which is what, 0.05, I believe, is what our significant level is. Yep. Then we must reject. So let's just do that again with color. If we plot our test statistic in here, we're going to have to reject. And if we plot our test statistic and we end up somewhere over here, we do not reject. So let's see where we end up. We calculated our test statistic, which basically looked at the sample means, sample means, took the difference of sample means and the sample standard deviations and magically turned it into this t-score. And so where does that go? 1.56, 1.5 is definitely less than 1.6, so it ends up somewhere around there. So we take this guy and plot it right there, which is clearly in the do not reject. So state the conclusion. Oh, nope, here, sorry. Determine whether to reject. Do not. Do not reject the null hypothesis. Okay, and then if you don't reject, well, then we have a wimpy statement. There is not enough evidence to conclude blah, blah, blah. Okay, let's do the next one. Once again, organize your data the best you can. And it looks like we're doing a low-fat diet versus a low-carb diet. Are low-fat diets or low-carb diets more effective for weight loss? A sample of 41 subjects. Which one is this for? This is for the low-carb diet. So I'm going to say low carb. Low carb diet has a sample of 41 subjects. And, we probably should have said the assumptions on the last one. Let me just go back to that real quick. Let's do our assumptions with a brown or some other color. Let's do that. Brown. No, let's go purple. What are the assumptions that must be satisfied to ensure that we have this uniform or approximate normal curve? First of all, we have our samples must be simple random samples from two populations. Okay, that happened. Second, the samples are independent from one another. Yes, I believe it said independent samples. And then the final thing is that each sample size is larger than 30, or its population is approximately normal. Well, I don't think it said that the population was normal, but it didn't really matter. We have evidence. Look at that. Our samples must be greater than 30, and they definitely are. Okay, so that first one was satisfied. And, we go down here. We're going to find out a similar thing as we look through it. Let's see, simple random samples. There it is. Nope, let's see where to go. I know I saw it on here. Simple random sample. Then the other thing was, okay, and then the other thing is that the sample size is greater than 30, and there we have 41 there. And then this sample, second sample, is 49, so that's good. Okay, and all right. So let's move on now. Let's go ahead and organize our data. We've got a sample of 41 subjects went on a low-carb diet for 6 months. At the end of that time, the sample mean weight loss was, so X bar was 4.6 with a sample standard deviation of, so S, because it's a sample standard deviation, of 6.28. And then it says a second sample. So the second sample is called a low fat diet with a sample size of 49. Their sample mean weight loss was 2, so sample mean is going to be X bar, 2.3 kilograms, with a sample standard deviation. You still know we're talking about sample, right? So the standard deviation is sample standard deviation of 4.66. Okay, now when they want us to try to prove something, that's going to be our alternate hypothesis, right? It says, can you conclude that the mean weight loss differs? There's the word, differs. And differs doesn't mean greater or less than, it means not equal to. So differs between the two diets. Let mu sub 1 denote the mean weight loss of the low-carb diet. So that means, if I'm going to go with my color scheme, that the population from the first sample, so we might as well do these sub 1 so we know it all comes from that first sample, is denoted with M sub 1. And then it says M sub 2 let's see, where do we go? M sub 1 denotes the mean weight loss on the low-carb diet. M sub 2 denotes the mean weight loss on the low-fat diet. So this one is M sub 2. And now, let's see what else. Okay, now we just said they differ, so let me do that. This would be our alternate hypothesis, right? We know that the null hypothesis is always going to have equal signs, so that's kind of easy. But the alternate is more the tricky one. And then finish reading this. Let's see, denotes the mean weight loss. Use the alpha, or the level of significance of 0.1 level, and critical value method. All right. So let's see if we can knock this thing out. First of all, we move on here, and we know that the population mean from sample 1, we're going to assume that they're equal. And then our population mean, our alternate hypothesis, is really the harder one to figure out, and there it is right there. If we can reject the null statement, then we're going to go with the alternate, which says they're different, they're not equal. This alternate hypothesis of not equal is going to make this to be a two-tailed test. Okay. Simple method. Once again, we go ahead and take a look at our different samples, sample sizes from both samples. The low carb is 41. N sub 1 equals 41. And our low fat is 49. And N sub 2 equals 49. And the simple method just says take the smaller sample size, which is 41, and then do your typical degrees of freedom is just going to be 1 less, so it's 40. And so my degrees of freedom is 40. Find the critical values. Round your answers to 3 decimals. If there's more than one critical value, separate them with commas. Well, this is going to be a two-tailed test, so yes, we will have more than one critical value. So some things we need to know. First of all, we were talking about before, you can see that this is a t-test or t-distribution. There it is right there. Also, by looking at the formula sheet, you'll see a t. So we do know that we're talking about t-distribution. T-distribution, we're going to need degrees of freedom, and we have that 40. We also need to know that alpha, I believe they said on this one, alpha is 0.1. But this is a little bit tricky. You got to be careful. This is a two-tailed test. And remember, with a two-tailed test, your alpha has to be split into both tails. Right, okay, so alpha divided by 2, and if you take 0.01 divided by 2, we get half our alpha equal to 0.05. That means this is 0.05 and this is 0.05. Right? The two tails put together makes your alpha, or your level of significance. So the beautiful thing here, what's really nice is with our t-distribution, the chart always looks for value to the right. So let's find this critical value, and then this one's just going to be the negative opposite of the positive side. So I need this value. I need 0.05, not 0.1. 0.1 would work fine if this was a one-tailed test. The alpha would be all on the right or all on the left, but because it's two-tailed, that alpha gets split, and so you have to use 0.05. Let's go check it out. And we go to our t-distribution chart, and there it is, and it needs to be cleaned up a little bit here. Come on, how come it doesn't work? There it goes. Okay, so let's use another color here. Let's go with pink. And what did I say? We're looking at so look up here. It says area to the right tail, and we want that area to the right tail to be 0.05. That's this guy right here. We already said that the degrees of freedom is going to be 40, so we got to go all the way down here to where it says 40. Come across and see where those two lines intersect. That means that t equals 1.684. 1.684. Okay, I think we found our critical values. 1.684 and negative 1.684. So the critical values are going to be plus or minus 1.684. All right, now we need to do our test statistic and see what to do here. Now remember, these are our critical values that we've got to use as a guide to reject or not reject. In fact, I think I'm going to put that up right now. If we end up in this region right here, yeah, okay, that's good. Then we reject. If we end up in this region right here, then we must reject. If we end up in this region right here, then we do not reject. Do not reject. All right, so let's see if I can do this. I need to calculate my test statistic. Remember, we can easily find that test statistic, right, for two sample hypothesis testing, difference between two means, and there it is right there. All right, let's go for it. I think I'm just going to go straight directly to color. I'm referring back to our information in color back here, right, where this is sub 1, and this is, I didn't put it down, sub 2. All right, let's start with, I guess, red. So, I already forgot, 4.6? Yeah, okay. So there's that information. We have 4.6, which is the sample standard deviation, or sample mean, and then we have our sample mean from the second population, which is 2.3. We have to find the difference of those two values, so subtract them. Down below, we're going to have a fraction that gets squared plus a fraction that gets squared, and we take the square root of all that and then find the quotient. Let's use our color. Our first one is going to be from our first sample. So standard deviation of the sample is 6.28, and that gets squared. And then the sample size is 41. Then we've got the sample standard deviation is 4.66, and that gets squared right there. And that's over the sample size on the second population, or second sample, which is 49. Putting this in the calculator, we get 2.3 up top. Down below, we get the square root of these two numbers. I'm going to show all the value I can. That would be 0.9619, 1219, 51, plus 0.44, 317, 55102. Take its square root, then divide. This gives us approximately 1.94033, and so on. Round to 3 decimal places, and we've got our t, our test statistic is t equals, round to 3 decimal places, 1.940. Whoops. 1.9, it's going to bug me, 1.940. Okay, so basically what happens is that test statistic came from our sampling data, and so now we've got to plot that. Where does it belong? Well, it looks like 1.9 is bigger than 1.6. It's, ooh, I hate that when it does that. Okay, there we go. It's going to show up right about there, which is clearly in our rejection zone, right? How can I make that clearer? If it's in this area, we must reject. If it's in this area, we must reject. And it's definitely in that right tail rejection zone, so we must reject. Okay, so let's see. Determine whether to reject. Yes, we must reject. So I'm going to just put down reject the null hypothesis. So I want to take a little bit of time because we're talking about two different populations, and it gets a little bit, this statement at the end gets a little bit confusing. Now this one just has this pull down menu, so it's not too hard. We just rejected, so there is enough evidence. But if you had to say all this other stuff, that gets a little bit confusing sometimes. So let me take a little time to try to kind of break down the logic of this, or how you label things. We had the low carb diet in red, and we had the low fat diet in green. Now remember, we had our HO, which is the assumption that those two population means are going to be equal. So that's our assumption, that the population mean from the first group is equal to the population mean from the second group. Okay, now we have something that we're trying to make a conclusion on, and that is the alternate hypothesis, which says that they're not equal. And so we're saying the population mean from our first group is not equal to the population mean of our second group. The only way we can actually get to this alternate hypothesis is if the data was so far out of balance that we're in this rejection region, and that's what happened here. We are definitely in the rejection region. So we come down here and we must reject the null hypothesis. Once you reject the null hypothesis, you're going to say this. And what did this mean in the language of the question of that problem? When we saw this not equal to symbol, that came from the word differs. So instead of saying that the low carb diet, the population mean of the low carb diet is equal to the population mean of the low fat diet, and this mean is how much the weight loss, we are now allowed to say that the mean weight loss of the low carb diet differs from the mean weight loss of the low fat diet. And you can see that right here. Now we're going to say there is enough evidence to conclude that the mean weight loss of the subjects having of the low fat diet, there's the word right there, differs from the mean weight loss of the subjects having the low carb diet. So with this particular one where it's just pull down, it's just is or is not. It's not as difficult, but coming up with all the language sometimes is a little bit of a pain. Okay, I hope everybody's doing fine. You can see it is 2:20 a.m. That's a little bit, I got to go to bed. So you guys have a good one and hang in there. We'll talk to you soon. Take care. Bye.